All right. Welcome, everyone. Today, I have with me my great friend and mentor, Eldar. He's going to help me a little bit behind the scene because this is my first time I'm giving a public talk. Eldar, could you please say a couple of words about you?
Yes, so thanks everyone for being here for Elena. I know she's really looking forward to the session. I know I am, and she's going to do amazing. So enjoy the session, and Elena, take it away.
Thanks. All right. So welcome again. My name is Olena Borzanko, and you can find me on Twitter. If you have any questions or comments, feel free to text me. A little introduction, I'm working in a company called Dus Express. It's a beverages delivery service in Germany. And I started in this company as a part of the logistics team where we were taking care of the order part. But now I'm working with the warehouse team. And I live in Berlin. You might have thought that I'm German as well. It might be shocking, but I'm not. I'm originally from Ukraine. And I got the idea for this talk after the latest event, which happened in my company, where I had an opportunity to learn, first of all, how not to use Cosmos DB. And I want to share this today. So I'll start from the story behind this. There were two companies on the market, and one of them is my company, Dus Express, and another one is a competitor of my company. So they were doing the same business, and they were doing great. And one day, they started the process of merging. And of course, even if companies are doing exactly the same thing, it doesn't necessarily mean that software can be integrated together as well. And we end up having completely two different architectures, and merging the software, which is extremely complicated process, was not an option for us. So one company was integrated into another, and for this last and least fortunate, it meant that amount of warehouses and users and the articles inside the warehouse and the load on the system in general significantly increased in a really short period of time. As we all know, software sometimes doesn't scale well, especially when we really need it. And that was clear for us that we should expect many new challenges. And who knew that one of them going to be a new warehouse system from the scratch? A chance to rebuild the crucial part of the running system is not something what is happening every day. So of course, no one wanted to have the same as before, but on a bigger scale. Business wanted to have something better. And when that kind of thing's happening and you have to build something new, which is going to replace something big, old, and a little bit legacy, it's not a case that someone's just going to handle you a bunch of requirements with all the necessary information. So we had no idea what to do. But it was also not a case that we can just sit and chill. No one had an idea how it should look like in the end. So we started to think how the processes should look like and how we can calculate our inventory, how we can track our articles inside the warehouse. Basically, how we can create a new design which is going to fit the needs of both companies. It took us a couple of weeks, and in the end, we came up with a couple of ideas. And it was the time to start writing some code, right? We can build a POC, we can take our ideas, we can validate them and see if everything works as expected. So we briefly discussed technologies we are going to use, but we were working in the same team for quite a while, so we were on the same page. Let's take Azure SQL, let's do microservices, .NET. I mean, everyone uses it, everyone does this, right? So no one had an idea to use something different. And up to the point when idea to use NoSQL database was thrown on the table. Why shouldn't we use Cosmos DB? And really, why not? It was a great fit. We had a brief look on it. Yeah, it looks great. For me, it was an opportunity to try something else, something different. So I volunteered myself out of pure curiosity to investigate this option. It was great to have an alternative solution or kind of a plan B, so later on we can make a comparison and decide what works better for us. I also remember I was talking with my boss, with my colleague. He told me something like, but remember that your query should consume less than 10 RUs. And with absolutely serious face and having no idea what he's actually talking about, I genuinely agreed with him because, well, actually, that makes sense. Should be quite efficient. But that was a moment when I realized that Cosmos DB is much more than just a database. So while we were building POC with the technologies we picked before, I also kept looking into Cosmos DB itself, trying to understand it better and how to use it properly. And I won't spend the whole session talking about how Cosmos DB is great, but I do want to mention a couple of things which I found quite important for my case and also for this presentation. So as you may know, Cosmos DB is a globally distributed, multimodal, and massively scalable database. Beside this, they offer multiple SDKs and multiple APIs to use. When I saw that I can start working with Cosmos DB, which is document database, document store, using SQL API, I was pretty happy about this because I'm familiar with this. I can start working right away. And I was wrong. We will see later on why. But for now, let's keep going in some theory details. So what is request units? This is something what you're going to hear quite a lot if you're working with Cosmos DB. And this is just a measure of computation cost of how much memory and how much storage and IOPS needed to execute your request to, like, for example, execute your query. Just to give an impression, because this is really abstract, but to give an impression what it actually is, if you want to read a document and you know exactly the ID of this document, and it has a less than 1 kilobyte of data, you're going to spend 1 request unit on this operation. On the other hand, if you want to write a document which has less than 1 kilobyte of data, you're going to spend 5 request units. So this is pretty important to understand because request units, it's not only a measurement of how expensive, what is the charge of your request, but it's also needed to understand how you're going to scale your database. And there is a couple of options when you create your Cosmos DB account. You can specify that you want to scale a scaling option, which is called serverless, which is based on consumption, or another option, which is called provision throughput. And when you select provision throughput option, you have to specify amount of request units which can be accepted per second. So if your query or request need to, for example, 10 request units to be executed, and your provision throughput set to 400 request units, it means that your database cannot accept more than 40 of those requests per second. Just an overview. We will have a closer look to it later as well. So once we created our account, we can create a database inside. And we have to specify what API we are using on the account level. On a database level, we can specify how we're going to scale it. If we selected provision throughput, if it's going to be a manual or auto scale. Later on, we can create containers inside our database, and we can also scale on the container level. To create one, we have to specify something called partition key, and it has 2 parts. The first part is the partition key pass, which is passed to a property in your document, which is going to be used to group your data by the value of this partition key. And if you can see, if you select a name as a partition key pass for your documents, they're going to be stored based on the value of this property. It could be A, B, C, it could be anything else. It could be the order ID, for example, or the customer ID. It could be any information which is exists in your document. And those groups, those virtual groups, they called logical partitions. So once again, inside your logical partition, you can store multiple documents, and all of them going to be stored by the same partition key value. In the meantime, the ID of each document should be unique. So keep in mind, if you will select a partition key pass as your ID, each of your logical partitions is going to contain only 1 document. And if you will go a little bit deeper in this structure, the next is the physical partitions. When I started to work with Cosmos DB, it was really confusing for me to understand what is the difference. So basically, physical partitions is just physical servers where your data is stored. And if you have a container where there is multiple logical partitions inside this container, it doesn't necessarily mean that the whole container going to be stored on the same physical partition. All your logical partitions can be distributed between different machines, and it, of course, depends on the amount of data. But what is the guarantee that your one logical partition would never be split between two different servers? So again, just to summarize what I said before, for each container, your partition key has to be a property that has a value which does not change. So once you selected the property path and you wrote this document, you cannot change this value of this property anymore. And you have to have a high cardinality, the wide range of possible values. This is needed to avoid hot partitions and to make the spread of RU consumption and data storage evenly across all your logical partitions. And this ensures RU consumption and data distribution across physical partitions as well. So another great feature of Cosmos DB is when we are writing some events, when we are updating documents, when there is a change happening in the system, there is something called change feed. It's basically persistent event store in Cosmos DB. It will save all the documents, all the updates which is happening in your system. And there is a couple of ways how you can consume this information. The first way is called pull model. And as name suggests, you can extract all those events from the change feed, and you can decide how you're gonna process them. This is the hardest way because you have to manage everything, starting from exception handling, how you're gonna deploy this. Everything is on you, but there is a great use case for this way. If you want to read data from your change feed one time, for example, to migrate it in another data store or to create materialized view for another consumer, this is a great way to go. Another one is the change feed processor. You can implement it using change feed processor library. And this is easier way because you can just subscribe on your container and those changes, those events are gonna be pushed to you. And then you can process them. Of course, in this case, you still have to deploy it, but it's much simpler than previous one. And the easiest way, in my opinion, is Azure Functions with Cosmos DB trigger. You also have to specify which container you're going to listen, and those changes also going to be pushed to you, but you just can publish it on Azure, and Azure going to take care of the rest. It's going to auto-scale, and well, it's pretty easy. We will see later how easy it is. There is more you can do. So as I said before, you can trigger an API call when document is inserted or updated. You can also have perform a real-time computation of your updates, for example, using Azure Stream Analytics or Apache Spark or Apache Storm or Azure HD Insights. There are plenty of options, and you can have a zero downtime migration of your database to another data store, for example, Data Lake or Azure Storage Blob, Storage Table, or another Cosmos DB. And what is also quite important to understand is the consistency level. It's pretty hard to understand in theory what kind of impact they have, but they have a really great impact on availability and latency and throughput of your application, of your database. So there is 5 of them, as I said before. And the first one is a strong consistency level. As name suggests, it has the highest consistency, but also a high latency, and on the other hand, pretty low performance and low availability. The next level is a bounded staleness, and it has a bit better performance than a strong consistency level, but it's still availability is pretty high because there is a lag in the replication speed. The next one is a session consistency level. This is pretty commonly used, and this is default you can get when you're creating Azure Cosmos DB account. This is pretty popular. This is pretty popular for like typical e-commerce applications or like social medias. And of course, there is performance, and the throughput is better than for the previous modes. The next one is consistent prefix, and it's pretty similar to the bounded staleness. The replica guarantee the consistency and the order. However, the data is not always current. And the last level is the eventual, and as name suggests again, your reads are consistent, but eventually. This is the weakest of model you can use, and this is pretty commonly used when the order doesn't matter for you of those writes, and the count is more important than the data itself. So, for example, if you want to count amount of likes or amount of comments somewhere, this is pretty good level of consistency. But of course, it all depends on the use case and what is important for the business. So, going back to our use case and to our POC we were building, we wanted to cover a couple of use cases. As I mentioned before, for us, it's really important to know how we can track our articles inside the warehouse. Basically, the movements which are happening, all the events. And we also needed to know what is the inventory, the current state of inventory, because when the customer is placing an order, we have to be able to say if we still have like those amount of beers or those amounts of water in our warehouse. And on the other hand, we also need to know what is the status of our storage locations. Basically, do we have to order more items, more articles, or maybe we have to trigger some refilling process for some locations. And just to show how does it look like, how those processes in warehouse look like, when the vehicle arrives with those articles to the warehouse, the first moment when it's getting registered in the system, this process called inbound process. When the articles move to the warehouse, they're usually stored on a special shelves. And of course, it depends on the warehouse and the business itself. But just as an example, those shelves can be separated in different sections. And the lowest section, which is easy accessible by employees, is called picking section or picking storage location. So employee can easily come there, pick an item, and move it to another location or another step in the process. And the upper storage locations, they called refilling. So they needed to store articles for the long term. And when the picking process is happening and the article was moved to another place, for example, maybe for the packaging station, or maybe it was moved to the handover shelf and then it was picked by a driver, the refilling process might be triggered and the articles from the upper shelves going to be moved to the lower shelves. So this is basically the movement we want to be able to store and to track in the warehouse. We want to know if those shelves are empty, and we want to be able to calculate our inventory like any period of time for all the articles. So at the point when we already built the first version of POC, we covered those use cases. And that was a time when I should try to integrate Cosmos DB itself. And because Cosmos DB has SQL API, I assumed that I can just easily swap those databases. Because we were using Azure SQL and Cosmos DB has SQL API, that should work, right? And it worked. I was able to write some data in the Cosmos DB, but when I was trying to calculate my inventory, like I did it in the way that I wrote some queries and I was calling them on demand every time when I needed to calculate my inventory. I was calling some queries, some aggregations and grouping, and it turned out to be pretty complex and expensive. And the number was not even close to 10 request units. So I want to show example how actually it looks like in the code, but just to set expectations right, I'm going to have a 3 version of demo. And in the first one, I'm going to show those queries. And this is kind of example how you should not use Cosmos DB. So just to watch as an example and never repeat. And of course, it's fine to have them, but you shouldn't execute them on a daily basis. The second version, I implemented change feed processor and I started to duplicate my data and create materialized view. And that was the point when I realized why we have this change feed, because it can reduce the cost by just duplicating our data significantly. And the third version, I just tried to use Azure function, and we're gonna see how easy it is to make it work. So let's go to our code. And we will start from first version. And as I said, I want to be able to create movements and calculate my stock on demand, and then later on extract all this information. So quick look of how we can actually write data in a database, where actually we start. We are creating our Cosmos client, and we just need to provide a connection string to our Cosmos DB and a couple of options. This is not required, so you can easily get rid of it. Then I'm creating my database if it's not exist yet, and then I'm creating my containers. While you're creating your containers, or you can also just get them if you're sure that they already exist, but I decided to create them. You can also specify the amount of request units for your container as an option. And the same could be done for a database. And for your container, you have to specify a partition key path. So this is basically the property which will be used to group our data later on. So when we did it, oh, I lost my mouse, sorry. When we did it and we are creating, we created our containers and we want to create our movements, what we're going to do is just, I'm generating some random data and I'm saving it in database. There is two points I want to mention. The first one, you have to specify partition key. Well, you don't have to, but this is a good practice, because if you're using .NET SDK, it will extract partition key from your object anyway, but this is just a like small optimization. And another thing is, if you don't need to receive a response, your newly created object, you can just say enable content response on write to false, and you won't get it. You will get how many request unit was consumed for your request, but not your newly created or updated object. The next thing is, if you want to calculate our inventory, I'm creating kind of a stock checkpoints. I'm doing here, I'm grouping my data by storage locations. And as I said before, I created my container and I specified as a partition key for my movement container as the article ID. And as you can see here, what I'm doing, I'm selecting properties what I will need later on, but I'm grouping them, first of all, by location and not by my article ID. So what is happening here is my query, first of all, extracting all the information from all the logical partitions and then regrouping all this data. So depends on the amount of data in my database, this query gonna cost more and more. And I'm calculating, this is just part of business logic, so I'm calculating kind of inbound and outbound movements, and later on, based on this information, I'm creating my stock checkpoint, and I'm saving this back in database. If I want to later on to read this information, I can simply specify which container I want to read and query this data. For the case of getting stock by locations, I will just extract all information from container, because I know that the amount of storage locations in my warehouse is going to be constant. It's not going to change. So it's pretty easy to just extract everything and do whatever you need with this later on. For the stock information by articles, because I didn't duplicate my data, I have to query it and regroup by article ID. So I will take my stock checkpoints, which I saved before, and I will regroup them kind of in the runtime. So going back, let's try to run it and let's see how does it work. I want to show what is happening now in our Azure portal. So I just ran it and this is version 1, and my database was created, and inside the 2 containers were initialized. For now, if we will check data, they're going to be empty. There is nothing inside, and the movement container the same, nothing in here. But you already can see that my article ID was picked as a partition key for my container. So let's create some data. Let's try to create 100 of movements. This was pretty fast. So as we can see, the request charge for each of my requests is 7.8 request units. It's not expensive, taking into account that the minimum you can get is 5 request units for write operation. This is pretty good value. So if we'll go back and check how our data looks like, we have the article ID and we have some randomly generated data. This looks pretty good. So what if we want to calculate our inventory now? As we can see here, I was showing before queries, which I'm using to group my data as a part of the business logic. And you can see here that one of my queries, the both of them actually needed more or less the same amount of request units. So it's like 7 request units to get outbound movements, and then 7 request units to get inbound movements. And then after all the calculations and aggregations, I have to save this result back in database. And each of these operations cost me like 7.4 RUs, which again is pretty okay. If we will have a look what is happening in our container here, we can see that we have some information by our storage location. So we now know that we have 2 Coca-Cola in our warehouse, and it's stored on a storage location with ID 555. So, all right, this looks pretty good. What if we need to read this information? This was pretty fast, and it's not actually expensive. So 2.9, taking into account that we extracted all the information from the container, this is pretty cheap. And the same for the articles, for example, 3.8. This is a little bit more expensive than the previous operation because we are taking the result of the previous operation basically and regrouping it. All right, so what if we're going to have more data? I'm going to try to write more movements, and I will try to write 500 movements. And my application is going to fail. This is expected. I just want to talk a little bit why it's happening. So as we can see here, we have pretty big exception, and we have too many requests, 429. So as I said before, we have to select how we're going to scale our database. In my case, when I created my database, default value of provision throughput was assigned, which is 400 request units. So when I was trying to create 500 movements, at some point, the cost of those requests per second exited allowed amount. So it was more than 400 request units per second. And this is a good example why having like expensive queries would also result in a bigger cost in the end, because if you want to have to be able to query big amount of data per second, you have a heavy read scenario. If your queries are expensive and they consume like 20 RUs per request, you will have to provision pretty big amount of request units for your database to make it possible. So what is a good way to, how you can basically fix it? You have to duplicate your data. So you're going to make your write operation a bit more expensive. You're going to create materialized view. You're going to save this information, but your read operation going to be super cheap. They're going to request a couple of RUs because query is already pre-calculated and saved. So the only thing you have to do is just to get this information, read it, and not execute it over and over again. So let's run my application again because it's failed. And still, let's try to write more data. So I will write another 100, and let's do another 100. It's pretty fast. So if I want to calculate my stock now, having around 300 or 400 items in my database, you can see that querying got pretty much like double in price. They got more expensive. And this is only like 300 or 400 items in a database. When you have a real warehouse system, they can be thousands of those movements per, I don't know, per minute, not even per day. So this is going to get more and more expensive with like in the same way as our amount of data increases in the database. So the request charge to save those checkpoints remain the same because it's the same operation as before. Only querying is getting expensive, depends on the amount of data. So what is going to happen with our read operation? Our read operation is still remain pretty cheap because we are doing the same as before. We're just extracting all the information from our container, and we doesn't care how many of those items in there. And to get the article information, it's still okay. It's got a little bit more expensive because again, we are regrouping this data, but it's still fine. So that was the point when we almost gave up with the idea of using Cosmos DB because we realized to make it work, we have to provision really a lot of our use, and the Cosmos DB is not cheap, so we expect it to be really, really expensive. But I decided to give it a try, and what I did, I actually used the main feature of Cosmos DB, which is called change feed. And I have a second version of my application, which is exactly the same as the first one, except that I'm not going to create a stock checkpoints on demand, and change feed going to take care of it for me. So I have my change feed. I'm going to run this, if I can do this. Yep. So now I can run my change feed, and while it's starting, I'm just going to have a quick look on the implementation itself. So as I said before, to have a change feed processor to implement it, you have to specify which container you're going to listen and how you're going to handle those changes. So you just get in the change feed processor builder, you put the logic how you're going to handle those events which are going to push to you, you specify the instance name, list container, and you build it, and you start it. Of course, after this, you have to deploy it, but that's basically what you have to do to try and play around with this. The logic to create the stock, basically to calculate inventory, is more or less the same. I'm making some pre-aggregation in memory because I'm going to receive a batch of events in the meantime. Like if I'm writing 100 movements, my change feed processor can receive a batch like 30 movements or like 40 movements, and then another batch of them. So I'm doing pre-grouping, pre-aggregation in memory, and then I'm just saving this information based on the logic like, okay, if I already have a materialized view, then I'm just going to update these values. If I don't have it, then I'm going to create a new one. So let's try to create our movements and see how it works with the change feed. We're going to create the same 100 of movements. And we will go to our change feed processor. We see that something happened. So the moment when I said I want to create 100 movements, my change feed processor was also triggered and started to execute some logic. So as we can see, request charge for creating a storage location inventory, the one word is missing, is 13 request units. And if you will have a look, it's pretty much the same for all the requests. So it's pretty stable, I would say. So if we will do more, if I would write more, would it change this value or not? Let's have a look. So I wrote another 100, and my change feed processor kept working. And as we can see, there is the same more or less value. So it's got 16, 15 request units, some of them around 14. So it's basically more or less the same. It doesn't matter how much we are writing because the change feed processor going to process only events which were getting pushed there, and it doesn't care how much data in the database already stored. Let's do another 100 just to make sure. Yeah, that's exactly the same. So if you want to read this data afterwards, it's going to be also super cheap because we already have all the data pre-aggregated, like our queries are pre-calculated for us. So we're just going to read this data. And it's request 1.0 request units. And if you will scroll up, there is kind of some data. So it's not like 1 or 2 items. Okay, so as we can see, the same is going to happen for getting inventory by articles. It's also going to be 1.05. If I will keep pushing data, it might eventually request. It might eventually get a bit more expensive if the amount of data going to change. But if you create your materialized view, which is best suited for your use cases, your read operation should remain pretty cheap, no matter how much data you have in your database. So I'm going to stop this application, and the last example we're going to have a look on, it's going to be an Azure function. So I'm going to use the same console application to write my movements in a database, but I'm going to use the Azure function to create those materialized views. And I'm going to run it. I changed the database name just to get this separately. And we're going to have a look what is happening in Portal in the meantime. So we see that our previous database was created, and we have a couple of containers in here. Just want to show how those materialized views look like. So we see that for our article, we have a document where is stored information on which location and how many of those articles exist. So we have like 5. We have some zeros because like we have pretty random data, but we also have some real data. So we know that now we have cola, and we have 3 of them on this location. The same is going to be for other materialized view. We will know how many articles exist on our specific location. So I'm pretty sure that my application already started and my database was initialized. Currently, it's empty. I already published my Azure function, and I want to start it. And I'll get back to my code. While it's starting, I will show how does it look like. So I created Azure function, and I called it movements trigger. What you have to do is specify a database name and, again, container, which your Azure function is going to listen to. You also provide a connection string for your Cosmos DB, and you specify a list collection name and if you want to create it or not. So this list collection, in case of Azure functions, is basically needed to monitor state across all your Azure function instances. And you're receiving the read-only list of documents and the logger, in case if you want to log some data. And what I'm doing here, I'm deserializing my documents to article movement object, and the rest is going to be exactly the same as I have a change feed. So I just move my code, and I know that what I can do now, I can just publish it on Azure, and it's going to be up and running. So the same logic, I made a pre-grouping, and then I saved those materialized views in 2 separate containers. In the real world, you might want to have 2 separate Azure functions for both of those materialized views, but just for demo, I keep them together. So I started my Azure function, and just because of its demo, I don't believe that it was started properly, so I'm going to refresh it. We see that our movement list container was created. And our application is also up and running. So let's try to create some movements for this case. And one more. If we will get back to a portal, we should see some more containers which were created automatically by our Azure function. And as we can see, exactly the same thing, exactly the same logic was executed, and those materialized views were created automatically for us. This is super easy because the only thing I did, I wrote logic and I just published it, and it's just up and running and it's working for me. So pretty easy. And this is the end of the demo, and it's already, we already were able to see how we can create materialized view with the change feed processor and with the Azure functions. And just to give a kind of a quick summary of what we actually did and what we saw today in the presentation, the SQL API should not be used as a traditional SQL as we got used to it. Like I always used to work with relational databases. So for me, writing a query is, well, not a storage procedures, of course, because you shouldn't do this. But to write query, it was pretty usual thing. And having a SQL API is great because you kind of feel that you can start working right away. But it's also a big minus because people making mistakes and making the Cosmos DB pretty expensive. Like all those requests, they're getting more and more expensive, depends on the amount of data, just because people sometimes don't understand that it shouldn't be used in the same way. So you can write some queries if you really need it, but you have to keep in mind that you should not execute it on a regular basis. So the next thing is creating materialized views and duplicating data is not a bad thing. This is exactly what you have to do when you're using Azure Cosmos DB, because this will make your read operations much cheaper. Of course, it depends on scenario, by the way. If you have a system where write operations are more often than read operations, then of course you might consider different options. But in our case, we knew that we're going to read quite a lot. We're going to have a heavy read system. But the writes, because our hubs and because our warehouse is operated by people, they cannot move that fast, like articles from one place to another. So we knew that write operations, they're going to happen quite often, but we're going to have more read operations. So we have to optimize our readings. And also make sure the data is distributed evenly. This is really important to avoid hot partitions. If your data, if you're gonna hit like only one logical partition or like one physical partition in the end, it will just increase the cost in the end. So make sure the data is distributed evenly, that you have wide range of values. And of course, keep an eye on the consistency levels. And there is also two options like single master and multi-master with the Cosmos DB. There is a lot of information in documentation, but it's also something what has a pretty big influence on the cost. So yeah, keep this in mind. And this is going to be the end of my presentation for today. But before we're going to end this, Global Azure has a virtual swag available. So feel free to scan this QR code, or you can hit me a message later on and do this afterwards. And I hope you enjoyed this session and it was helpful. Again, feel free to contact me in case of any question or comments. And have the nice rest of the conference. And now I guess, Eldad, you can join me back in case if there's any questions.
Yes. So first of all, amazing session. I'm looking at chat. I think everyone is really enjoying this. We already have one question in, so let's start with that one. And in the meantime, people, of course, can post more questions.
Okay.
So
let's say you had another view after data is already there and you need a new run over the change feed. Can you consume it from the beginning or only run it on the new data that arrives afterwards? Yes, actually, that's another great point of change feed, that because it's a persistent storage of your events, you can rerun it. You can travel back in time. You can rerun it from any point of time. You can rerun it from the very beginning because all your events are stored in there on a persistent basis. So yes, if you have a new consumer and you have to recreate materialized view for this consumer from the very, very beginning, you can do this easily. Or for example, if you made a mistake in your current materialized view and you want to rerun it with a new logic, you can also do this. And what I really like about change feed, that it also can be used for testing, for example. If you're making some breaking changes or you are changing your logic, but it should result in the same kind of materialized view, you can rerun it and see if your system behaves in the same way, or if it doesn't behave, then what actually happened in there.
Makes a lot of sense.
Yeah, I hope so. That's why we're here today, isn't it?
Yeah, so I don't see any other questions yet. So let's give it another minute or so to see if there's anything else popping in. So how did you like your first session, real life session?
Yeah, this is amazing. I kind of feel that I don't remember how it started and how it went. So because I felt pretty nervous, but I really enjoyed the session and I hope this was helpful for people. And people were able to learn something new. And also, by the way, because it's my first session and you as my mentor helped me a lot, tomorrow we're going to have our session together where we're going to share our experience, me as a new speaker and you, Eldad, as my mentor, right?
Yes. So that should definitely be a fun session, which will be at 6:20 Amsterdam time tomorrow, or Berlin time as well, of course.
Yeah, Berlin time as well. That's true. That's true.
So yeah, definitely invite everyone there. And like I'm looking at the comments, like everyone is saying that you have done a really great presentation. I can only agree on this.
Thanks a lot. All right, so I think that we can end today's presentation. And again, I'm always available for any more questions or comments. And have a nice rest of the conference and rest of the day. I think that we can finish for now.
So thank you, Elena, for your great session. Thank everyone for being here for her.
Thank you. Bye-bye.
Bye.